one thing I have forgot is to properly introduce Peter, and so let me introduce him. He studied applied physics at KTH in Stockholm, and he's a senior group executive with about 30 years experience as a CEO, but mainly in the high-tech industries. You can see his full career on LinkedIn if you want to follow that up. He's had both large company and small startup company experience, spanning software, artificial intelligence, machine learning, etc., hardware and infrastructure as well. He holds about 13 patents and patent applications. So without further ado, thank you for joining us, Peter. Please take it away with the slideshow.
Thank you. All these senior people on this call are quite scary. So let's see what we can do. Let's have some fun. There's a lot going on at the moment in the world of AI, as we know. And let's have a look at the way that looks right now and where it takes us. I think it's necessary for us together to try to assess what the future does hold. And that needs dialogue among people who think about what the future will look like. It's a little bit complicated. And would that it were so simple that we could just draw straight lines of where the world is going to go, but that's not the way it is. So it's complicated. So let's look at that together. My background, well, you can find me on LinkedIn. That's a QR code for my LinkedIn. Please feel free to connect. And next time I'm in Adelaide, if anyone fancies going offshore fishing or having a game of tennis or football or maybe the occasional hand of Texas Hold'em, then those are my interests. And also the interests of my 3 wonderful children. So we share all of those joys. That's my background. So let's start with an architectural framework for this conversation. Applications at the top, those are things that people do with AI, and at the bottom we have places where we execute those applications. Obviously, those applications are broken down into many small jobs, but ultimately, I think we all agree that the applications need to run on some chips somewhere. Now, between those 2 layers, the layer of people seeing the service operating and it being executed on a chip, there's a bunch of software. So statement number 1 is that having access to the source code is good, because if you want control of your infrastructure, of your world, then closed black boxes are not great fun. And source code comes in a couple of different flavors. It can come in the flavor that it's open source, or it can come in the flavor that it's part of a license agreement or supply agreement with your partner that's doing your technology for you. But it doesn't really have any value from the perspective of being in control unless you have own competence within your organization. And that's something that I often find interesting, that people want to have the source code, maybe the source code in escrow, but they actually don't have the competence to understand what that is. So effectively, they're not in control of their digital destiny after all. The next thing is, in terms of these applications at the top, if we look at the ones that succeed, I mean, most AI projects fail. Let's be clear. So 95%, I don't know what, most AI projects do fail. And in my view, and talking to people, the typical failure mechanism is that the whole project is focused on cutting cost as opposed to increasing value. And the projects that succeed are typically characterized by an approach to developing the system, which is all about melting all the assumptions that we used to have, and then starting from what do we deliver to the customer, what are the actual fundamental things that we need to do, and then working from there. So that's typically the way that you succeed with these AI projects. So let's start from the bottom up. Let's look at the chips first. And for chips, I'll use the acronym GPU instead of chip. Fine. These GPUs used to look like this on this picture, and they used to fit into quite a big room. IBM did really well. They started off with hardware, then they put software on top, and then they moved up the value chain, ultimately moved into consulting. So they had several decades of a very successfully executed business model. Obviously, everything you see in this picture is now simply a feature in a phone. At the time, this was the state of the art. The Nvidia systems that we're also impressed by right now, and should be, are liquid-cooled systems that physically take up roughly the same amount of space. You can't put these in a smartphone right now. They're a bit too big for that. They would need to be 1 million times smaller in order to fit inside a phone. All right, so let's look at that for a moment. Moore's law says that the silicon density, the transistor density on chips doubles every 2 years. However, the speed of developing the hardware is moving faster than that, because there are other effects, such as how you use these things, that accelerate development. So the underlying hardware performance is doubling every 6 months, approximately. And that's taking into account things like energy consumption and the way that the chips are designed, not just the number of transistors, but also the design methodology. So there's a doubling roughly every 6 months. Okay, so to put that thing inside a phone, it needs to be 1 million times smaller, just to grab that number again. Well, 1 million is 2 to the power of 20. And if things are doubling every 6 months, then it means that that system can be put into our phones in 10 years from now. That's realistic. That's a realistic statement. It's not crazy. And that is the future that we're moving into. We are moving into a situation where the computer that will be in our children's phones, laptops, whatever else, is going to be immense. The computing power in cars, in any electronic system, is going to be absolutely immense. And we will look upon this box that we're seeing on the right-hand side in 10 years' time in the same manner as we look at the incredibly good IBM system that was designed before we were born. The next system I'd like to look at is the Shanghai Cube. This system is designed on a different basis. Going back to Nvidia, they're following a strategy which is similar to IBM. So they're doing increasing value add all the time, moving upwards the value chain in software and so forth. The Shanghai Cube is built on the assumption that the supply of top chips or GPUs is not stable, that you need to use multiple types of chips underneath. It's built in collaboration with a number of different people. So the whole philosophy and the design of this system is more similar to an open source community as opposed to a traditional high-tech environment. The Nvidia system has higher performance, but this is it's a really, really interesting system that's been built in Shanghai called the Shanghai Cube. It's really powerful. It is an interesting thing. There's a very different way of building things. The next place where we have reason to expect to see a lot of computing power is in telecom base stations, because the latency and the communication path resilience, when you start increasing throughput, will drive a lot of computing power out to the edge. So the role for telecom companies might exist in the future by embracing these things. I think there's a real opportunity for telecom companies to move in here. So edge-based computing, I think, is going to be a big thing. So those are big things. Good. So let's go go further into that to further understand exactly what's going on. So if we assume that we have multiple types of physical GPUs that sit and process everything that we do, what we need to do is we need to put a layer of virtualization on top of them so that when we build our software, we build our systems, we can do it in a manner which is agnostic about the physical silicon, so that we can operate our services both on the IBM box, the Nvidia box, the Shanghai Cube, and also in telecom towers. We want to be able to do all of those things from one centralized software system. So we do that by hiding each GPU under a software layer, and that works really well. So virtual GPUs or vGPUs are an important tool, and we'll go back in. I'm going to go into the detail of why that's important shortly. From a software perspective, it means that each vGPU is one single logical, and it means that you can swap out processes and add more capacity underneath all the time. So this is an important layer. Next thing we do is we put a Kubernetes layer on top of that in order to start having a place where we can put our apps, or strictly speaking, the jobs from our apps, and get them executed. Now, I'm kind of jumping to the conclusion that we're going to do this with Kubernetes, but that's not quite true. It's not really a wild jump, because I just observe facts. The fact is that the majority of deployments, cloud-native deployments, are built using Kubernetes. So it's a de facto standard. The good thing about standards is that there are so many of them. That's something we used to say when I worked at Nokia. Kubernetes has become a standard that people do adhere to. And for that reason, I think it's worthwhile taking that seriously for all of us. Kubernetes has a number of beautiful things inside each cluster. So you take jobs from the apps, and these jobs from the apps are placed inside so-called pods within a Kubernetes cluster, and then they're executed. And the control plane inside that Kubernetes cluster can then put the job in the appropriate place within the virtual GPU. So there's a communication there, so that you can start slicing the underlying physical GPU so that you can get a higher utilization level. And that's important, because you do want to be able, you don't want one single job to hog the whole GPU, because that's a waste of power. So you want to be able to slice those things in different ways. So this is a really, really beautiful architecture for placing applications in different places, because these might indeed be quite different places. You might have one fintech application or one smart city application, and you might actually be spreading that out among data center A, data center B, on-premise or out on the edge. Let's see. We need a logic for that, and boom, we have it. We have a multi-cluster control plane. So it is indeed possible to develop one digital energy application and deploy it via a multi-cluster control plane in such a way that different tasks go to different places. And so you end up with the jobs in all of these different places at the same time, according to some job scheduling, according to some rules, some policies, so that things land in the places where you want them. As you can see, this architecture has evolved quite a lot. You might actually be running some things on premise within your business and some things on the AWS cloud and somewhere else. You might have quite different places where one application is running, but the job is running in different places. Of course, you need to consider the runtime implications of that, because it's not just a syntax check when you make your deployment. You actually need to think through the runtime and the operations side of it too. Good. So to make that work, you need data orchestration policies inside the multi-cluster control plane, and that does happen. And that enforces locating services in appropriate places, because You might have multiple places where you can put a particular application, but if you're not in sufficient control of some of the locations, then you can't deploy there. It doesn't work anymore. So you might have some applications that can be placed in non-sovereign places, but if you're running something like an energy grid or a utility company, then that might be mission critical, and for that reason you can't just put it somewhere where it's not in your control. So you have to think twice. And you do definitely want to have unified governance over the whole thing. It's complex, and you do want to be in control of where things go. And that comes straight into what we spoke about before the call this morning, that the security implications are fascinating. I'm not going to go through the technical questions of how you implement specific security features. What I'd like to do is touch on another angle. First of all, the statement that everything is vulnerable, including employees. Everything is vulnerable in an ecosystem. And when people construct attack vectors, they construct them with a very open mind. It's a bit like someone who's obsessed, a pedophilia, I don't know, someone who's totally obsessed. The people attacking whatever we build are people who only think about attacking what we build. It's the only thing they think about. They are absolutely obsessed with with attacking the system. And whereas we spend some time thinking about security, then we think about something else, and then we go back to thinking about security again. So that's quite different. So the attack vectors are going to be done by people who are hell-bent on attacking the system. They really are. And in so doing, they will be combining different things to attack. The most elegant attacks that I've seen on systems have been in financial systems, and they have combined elements, communication structure, locations, humans' reluctance to act, and so forth. They've combined these things in really, really innovative ways in order to succeed with their attacks. And it is very complicated to defend these things. If we look at the attackers, they might have different motivations. So second guessing why people would do something is a difficult thing, because they can do it for money, they can do it for hate, they can do it for fame, they can do it for many reasons that we don't quite understand. On the money side, buying and selling information is business, and buying and selling business data is interesting, even if the data is well encrypted. If you look at the timeline of RSA bit length for encryption, by way of example, 512-bit RSA key lengths were not very long ago, but they're reasonably easy to crack now. Currently, most people are building at 2048-bit keys, and the recommendations in 2030 are expected to be that it's for 3072-bit key lengths. Now, all of those are of interest to people who buy and sell data, because in the future, computing power will be such that it will be possible to do brute force attacks on things that are secure now, but will not be secure then, simply because computing power is going up so much. So, well, what would that be? Well, a simple example, if I can get a 20-year-old database with pension details, with full pension details, then it will be possible to do lump sum pension withdrawals from people's accounts and get that transferred offshore. So stealing people's pensions will be possible if you can do that. Similarly, unless new systems are put in place to protect. But the business processes around that are difficult. Attacks like that will be possible. And similarly for governmental information, governmental information, can be of big value, even if it's 15 years old or 20 years old. So we should expect to continue to see a strong trade of databases that have been stolen. That's going to continue. Right, so let's go back to the fun stuff. Well, I do think this attack vector stuff is interesting, but let's go back into building nice systems again. So one of the key elements of the multi-cluster control plane is the ability to have flexible policies related to your business, where those policies decide in which pods the applications are deployed in. And in order to make that work, the Kubernetes cluster fleet itself, the different parts of the Kubernetes cluster fleet, they advertise their capability up to the multi-cluster control plane. So they tell the multi-cluster control plane what capabilities they have. And there are particular conventions around labeling and discovery. You might, for instance, in the third case at the bottom here, you can see GPU.mig, etc. So that's a typical Nvidia chip telling us what its capabilities are. But in general, we can say that the characteristics of the underlying silicon needs to be brought up to the multi-cluster control plane so that the multi-cluster control plane can use its policies and place apps in the appropriate places. And because you do end up with a situation where applications do live in multiple different places. Here we have a situation with 4 clusters, and one cluster is suddenly not available. So you need a dynamic redistribution of all the jobs that were there. So the multi-cluster control plane needs to be capable of lifecycle management, so that you're running some jobs are being executed in Sydney, some jobs are being executed in Singapore or somewhere else. So you need to be able to chop and change and move those at full speed. And that capability does exist today. And the way that works to make it go in both directions is that from the top level, the applications, be it fintech or AI training, AI inference, or data jobs, or digital energy, or smart city, whatever that is, those applications declare their intent to the multi-cluster control plane. And then by marrying the underlying availability that's been advertised and the top level requests, it becomes possible for the multi-cluster control plane to put the right place in the right job in the right place. So sovereign apps might go in one place with approved hardware and so forth. There might be some jobs that simply need to be done cheaply. Good, so that in the cheapest acceptable GPU. Noisy neighbor prevention is done with a technology called DPU. And what that means is that if you're running your digital energy application within a cluster which also is doing AI training, then the AI training might be eating vast amounts of capacity, and in so doing it might be eating up the capacity that you need in order to operate the energy infrastructure for Adelaide. So the noisy neighbor feature is something that does need to be managed. And the technology that's used for that is something that's called DPU. So it's an important feature that's needed as well. All of these things need to be standardized. So I put a logotype in the top right corner here, Cloud Native Computing Foundation, CNCF. That has evolved into being one of the fundamentals for the standardization of this. I earlier a little bit humorously said that the good thing about standard is that there are so many of them. Well, that's certainly true, and it's also true within the CNCF, but it is good that there is a body that does standardize lots of things within this. So the methods of doing virtual RAM or VRAM, the methods of doing virtual GPU, the methods of doing virtual inference, all these things need standardization, and that happens within an open source community called the CNCF community. It's a really powerful organization. Good. So let's look at GPU optimization for a moment. That comes in many flavors. So we have sharing GPU slices. So you take a big GPU and slice it up in multiple ways in order to be able to deploy loads in an appropriate way. Again, I mentioned earlier that that needs to be done in a manner which does not create noisy neighbors. And if you do those things in the right way, then you can increase the GPU use by a lot. So like 2 or 6 times, if you use the right technologies for this, then you can accelerate your GPU a lot. And it causes fewer idle GPUs and lower power consumption, lower capital expenditure. So there's a lot of optimization that can be done from a software level in order to make these things work well. And for that, you need controlled sharing and predictable latency. A lot of applications don't need to be super fast in terms of the latency. You can let it take 1 millisecond, and it's no big deal. But some applications are super sensitive in terms of latency and so forth. So again, these things need to be communicated. The apps need to say what they need in terms of performance, and the underlying systems need to tell the multi-cluster control plane what the likely performance is going to be, and so that you actually do end up with the type of performance that you want. And this does cut in 2 ways, because compute optimization is not only a technical optimization, it is also economic. And I'm going to go into the money side a little bit later on, but it is expensive to run these systems. If you're doing a lot of AI training, the invoice does add up. So optimizing not only for the technical aspects, but optimizing also for the economic aspects of computing is super important. Right-sized provisioning, license costs, using idle capacity in different ways, running some jobs overnight when no one else is doing it. And also automating the way that all of this is operated, so reducing the human costs by having various automation systems that mean that we don't have to have too many engineers doing everything. That's super important as well. In terms of data, data can be spread out over multiple data centers. You can have a full data mesh. And if you do that in a structured way, then people typically talk about data fabric as being the structure for the mesh. So, okay, working out where to put the data, which paved roads to use in order to get high speed when you're moving data between different data centers, because they do, or different even Kubernetes clusters, you need to work out how that's going to be efficient, because if that is going to be, if the system needs to perform well, then how you handle data is a fundamental issue. In the old days, we used to talk about single point of truth for all data. And I say old days because I mean 12 months ago. A single point of truth is still, in some contexts, a really valid way of looking at it. However, when you do high volumes of work, it doesn't need to be a single point of truth. It can be a distributed mesh data with Fabric instead. It becomes a bit different. So it can be, it doesn't have to be a single point of truth. As long as you get an answer, a result which is right with, say, 20 digits of accuracy, then that's good enough. So there we are. And so we're moving away from the single point of source of truth statement towards distributed mesh data with Fabric instead. That's a change. Now, let's look at LLMs for a moment. I think we should just make sure that we all have a shared understanding about those things. So an LLM is a summary. One way of thinking about it is that a large LLM, large language model, so a large LLM, it's a bit like a summary of all of the internet. And you take everything that you can find, and then you summarize into say 1 terabyte of pre-trained material. And if you do that comprehensively, then it'll cost maybe $100 million in computing power, maybe $200 million in computing power. If you do a bit less, then it's still $10, $20, $30 million for one run. And for that reason, ChatGPT doesn't update itself in real time all the time. What happens instead is that they do batches, and then they have different methods of strengthening those batches so that it still feels as though it was real time, but in fact it's not. The effect is, say 1 terabyte of intelligence, if you wish, but this is like having a friend who's very decisive and also quite vague up to a particular cutoff time, and that's a characteristic of a large LLM. And then in order to make these things sound a bit more reasonable, you do post-training to get the appropriate tone of voice. And that works really well. We've all tried those things, it works really well. The thing that's happening, though, is that people are using these LLMs not only as large LLMs, but they're also using small LLMs, because you can generalize a token sequence to not only be a sequence of characters or a sequence of words, but you can think of that as being a sequence of activities. So you can use small LLMs in order to automate particular industrial workflows and so forth, and that does work. So smaller LLMs comfortably fit inside a smartphone, so you can have 20 LLMs. All of us that have phones on this call can have 20 LLMs in our phone each. And those 20 LLMs in our phones, they can do different tasks for us. So I think most of the LLMs in the future will be small LLMs, which are perhaps orchestrated by larger LLMs. So that's going to break up, and that's changing quite quickly. And if we then move on from there, then, okay, hold on. In that case, we need to work out which LLM we should be using for which application. And yes, there are systems like that available already, where you can have a library of LLMs where you're choosing different LLMs for different outcomes. And you can have features within multi-cluster control planes. So Dow Cloud is excellent at all of these things that I'm talking about. Just to take one example of a place where all of these things are available is most extraordinary. So you have a library of LLMs to do different tasks, and you end up being able to automatically route requests to the most appropriate LLM, and it's powerful. You can actually do very much with these things now. And you then come into a quite interesting situation. Let's assume that let's assume that you're running an insurance company, by way of example, and or a pension company, by way of example, and you're using these methods in order to automate aspects of your business. If people then challenge you and said, but hold on what basis did you make that decision a number of years ago? Well, you need to have a method of automatic fall. First of all, if you do something wrong, you need automatic fallback that happens really quickly. So that technology is interesting in itself with modeling and caching and so forth. But you also need to be able to roll back 10 years in order to verify that what you said back then did match and so forth. So this becomes complex, and don't worry, it will get worse. And same thing with latency associated with inference. So if you have customers who ask questions, then you want to be able to answer the question within a particular timeline. And when you build a system, which is a high volume system where you have, say, 100,000 concurrent users, then modeling how to minimize the latency and cost at the same time per AI request becomes really quite interesting, necessary. And we can all see that because we can all go on to these systems and ask, please, can you draw me a picture of someone chasing a giraffe? And that takes a lot of computing power. So you want to be able to deliver that response quickly enough, but you also want to do that in a manner that doesn't hurt you from a cost perspective, and it can do. Some of the requests that people ask for are requests that can cost $5 just for one request because of the underlying computing power required to perform that task. So the money side is necessary. It's absolutely necessary to optimize for both the economic aspect and the technical aspect when you build these systems. So where are these things going? Well, we can talk, and if we talk, then that can be converted to text. If it can be converted from text, it can go into an LLM. Underneath that LLM, we can have a vast array of things. We can think of the LLMs as being a user interface to the rest. The LLMs, of course, themselves are entirely unintelligent. And we can also empower the LLMs to take actions on our behalf. And if the LLMs do take actions on our behalf, then after taking that action, the LLMs can output text that then is converted into sound, and we can talk to the systems. So in the future, we will be able to talk to the factories and schools and so forth, and positively interact with them. That does change things. So the person on the top right on this image here is wearing glasses that have built-in 5G communications capability, two-way. And with that, it's possible for that person to talk to a customer while being listened to by the company that she works for, which means that it's possible to have a dialogue where she asks, do we have the blue M9 in stock? And while she's talking to the customer, the factory responds using the bone conduction speakers that those particular glasses do have. Those are production glasses. And responded by saying, yes, we have 7 in Munich, which means that that salesperson can, in that person, reply in real time to the client and, in fact, place an order. So that's a voice-driven way of controlling all of the factory. So it will be possible to sell cars like this using executable conversations. That's definitely coming. And we can then generalize that a little bit and say that, well, that's true about every type of company. So we have groups of people or one person, and they have an interaction with the company that they work for or the university they work for, what have you. The request, response, they might be machines or they might be humans, they might be agents, they might be whatever. But in all cases, they do end up having some type of a user interface into a system. And inside that system, there is kind of the corporate brain, meaning there's an orchestration of going into all the activities that are being taken care of. So if you're building an agricultural, if you operate an agricultural site, then the feed amounts, the watering amounts, the speed of growing and so forth, all of those can be modeled in different ways. We have customers, we have forecasts and so forth. We have the weather reports coming in. So based on all of those different models, that can be brought together and orchestrated in a central place. And that's kind of the corporate brain that learns from absolutely everything and has its own LLM libraries and models and so forth, and is then able to serve the things on the left, which can be either humans or agents. So the way that these corporate brains are going to be constructed in the future will be core to each business. This is where the action will be in the future. There's going to be a vast number of models on the right. They will be brought together and orchestrated, and it means that the whole entity that's operating will have some behaviors. So let's look at those one by one. And first of all, we're all familiar with Albert. Of course, we feel that we know him really well, and we're also familiar with the statement that doing the same thing over and over and again and expecting different results is insanity. We're comfortable with that. If we turn that upside down, then we have sanity. And sanity is when we do the same thing over and again, and we do expect the same results. And that's machine learning. Now, machine learning may feel a little bit underwhelming when everyone's talking about these really exotic AI systems. But just like small LLMs, machine learning is a Lego block that will not go away. It will be, the majority of what we do will still be based on machine learning, small LLMs, and so forth. And then we build more complex systems by combining lots of these. So if we want to be involved in the technologies that this talk is all about, then understanding machine learning is basic training. It's if we don't understand the fundamentals of machine learning, then we're in the wrong place. Absolutely necessary. And when we develop these machine learning systems, we need a development environment that is able to do it. Because with machine learning, you both have decision trees, and when you then pull together a whole bunch of decision trees, you end up with a decision forest. And when you have decision forests, you actually have a really powerful system. It's not to be joked about. You can do very much with machine learning. Decision forests are really, really strong things. What we do need to do, however, is to have machine learning development environments where it's possible to do this in the appropriate manner. So there's the model development. We need to train the models. We need to manage models, so lots of different model versions. Like I said, it's a decision forest, so there will be parallel models that do different jobs. Those need to be brought together and then deployed, and then we want to get the results coming out of those things. And that's tricky because we need audit, we need policies, we need governance and control. And we need to work out where these things are being executed. So this is a multi-level challenge. We spoke about the importance of deploying in the right place earlier. Well, that's also true for specific machine learning models. We need to know where those things go. And so machine learning development environments are important for us to succeed. And let's move towards AI. And I have a good friend, David Zeitlin, who is a professor of anthropology at the University of Oxford. And he's written many books, including this one, Understanding Social Images. And I actually think that his work at the moment is relevant for the way that we approach the next generations of these systems. I don't know if I should call it AI or call it. We have discontinuities in our lives, and when there's a discontinuity that comes along, in my personal experience, the best way to handle discontinuities is to make the assumption that we are the last people to see the discontinuity. And if we make that assumption, then it's more easy for us to immediately start living on the other side of the discontinuity. Assume that it's already hit us, and then it's easier to handle these discontinuities. If we look at the perception that we can have right now, then we can have perception that's based on data in different formats, of course, images, if that data is structured in some ways. It can be audio if it's structured in some other ways. It can be video. If we combine the images and audio, we end up with something that we call video. Great. If we take all of those different types of perception, then it's possible for us to start building models about how we handle our world. And you can call this world of coding or whatever you want to call it, but there will be entirely new ways of thinking about how we code and how we model things. And we need to melt down our assumptions about how that should be done and reimagine the way that these should be done, because it's not the same. The computing power that we will have in our hands within a very short period of time is such that we can do things in fundamentally different ways than we do today. And we need to take this complex world and simplify it, but not oversimplify it. So it's the world will change. The way that we model things really will change based on current know-how, which is absolutely state of the art from our perspective and will very shortly be viewed as being ancient by future generations. Meaning, if we go an incredibly long distance into the future, such as 5 years, then everything I'd say now will be viewed as being ancient. So the current methods assume that we have libraries of different AI models. Depending on which model we choose, we end up with different results. So at the moment, there's an engineering skill in choosing the appropriate model to model the appropriate thing. And all the current AI models are very similar. So you have a big problem, and you decompose it, different, smooth it, regression, and then you combine everything in order to get some type of result. They work the same. They function, but they are very, very different. But at a high level, they're actually surprisingly similar. So you can take univariate time series when you do El Nino calculations, for instance, and there are several different models with which you can do El Nino weather predictions and so forth, and many of them are good. And it's a Python type of coding world that you're in at that point. If you look at the Facebook models that they used for modeling user behavior, enormously powerful. It is open source. This is stuff we can use. Really powerful models for modeling user behaviors. If we organize a dinner party where we have a table with lots of people, then we might put everyone who's interested in cricket at one end, and we might put everyone who's interested in playing tennis at the other end. And they can have wonderful conversations, and at the end of the night, everyone mixes and feels happy. That type of clustering of human behaviors to create what's technically called echo chambers, where people of similar opinions can share their opinions with each other and feel gratified. All the technologies for that sit inside the Prophet model, and it's really, really powerful. And it can be generally used. You can use it for fish farming. You can model many groups of things with this model. Really powerful. The ARIMA model is in a way quite similar to what I just said, but it's used quite often, for instance, in the oil industry for capacity planning purposes. State space model means that you have one world of models that sit on the outside, on the observable space, and then you have one or more layers of models for things that are not human observable. and you model those separately. And once you've modeled them separately, you connect them. That's the basic idea with state space model. Many situations where that's highly applicable. VAR is another way of doing Bayesian structural time series. It's a powerful method as well. In general, these social media algorithms are all about amplifying existing emotions. So detecting emotions and then amplifying them in different ways. They are multi-layered models that they use, those guys. LLMs, we spoke about already. These are, I think, going to stay with us. I think LLMs are going to continue to be an important element. To what extent the LLMs become pure user interfaces, I don't know. I think a lot of the lifting will be done by the heavy mathematical models underneath the LLMs. And that's something that's often called RAG. In this image on the right, there's something called a crocodile, there's something called Jack Ma, and there's something called a unicorn. I'm aware of these things. I have not seen a crocodile myself. I've seen an alligator, but I've never seen a crocodile. I haven't seen Jack Ma, so he may or may not exist. And I have not seen a unicorn, may or may not exist. I don't know if those three things exist or not. Hallucination management is something that's done with RAGs. So some of those may be real, some of them may not. I don't know. I'm a physicist. I have to go based on my own observation. Regardless, you end up in a situation where you have ensemble forecasting or ensemble management of systems where you take all of the above, all the different models, everything that you possibly can dream of, 52 different LLMs, everything else, and then you make agents. And these agents are then able to perform tasks for us. And the way that we construct these agents depends on what we're trying to do. It depends on the music that we're trying to create. The instruments we use depend on the music that we want to build. So this is going to be increasingly complex. There will be so many new ways of combining these things, and we need to be good at all of those things. Great. So this is similar to the situation at the beginning of the 1950s, where this product, this atomic energy lab, was made available for sale to children. And before we humans exploded the first nuclear bomb, we didn't know if exploding the first nuclear bomb ignite the atmosphere. We simply didn't know. But we tried it, so we pressed the button and it did explode and the atmosphere did not ignite. So that's good. We have, and we had the confidence to start selling these kits to children shortly afterwards. This kit came with its own uranium-238, which is the longer-lived isotope, and included in the box, very handy. So we will now have AI development kits where the significance of these AI development kits may be similar, because we are building autonomous systems and we don't know where these autonomous systems will go. We really don't. So fine, let's do it. So we need environments where we have full data science and AI environments fully integrated, where we can run projects that go all the way from IoT to very large data centers, where all of those are brought together. And those development environments need to allow hundreds of developers to co-develop in parallel with each other without causing chaos. So we need isolated spaces for each developer, and we need to be able to enable each developer to achieve reproducible and persistent work, so that you can quit one evening and continue in the morning, and the same work is still there. You need to be able to roll forward, roll backwards. You need to be able to audit. In terms of running up costs, absolutely need elastic scale up, scale down for all of this, and data location control and so forth. These data science and AI environments are complex, and they do exist, and they are extraordinary in the level of control that is achievable. This is necessary in order to achieve the type of performance that we are talking about. Very, very, very powerful. The previous picture that I just flashed back to is applicable. And cloud edge collaboration is very important as well, because in developing these systems of the future, we're developing a system where our garage door will have the computational capability of a big computer. And when we deploy these systems, we're going to be deploying onto everything, the garage door, the kitchen, fridge, whatever else. So all of this is it'll be very fluid, and we will deploy in far edge sites, regional sites, central data centers. All of those things will happen at the same time. We need to be able to test those things, and it's beyond simply testing, because we also need to think about the operations side of it all, because the underlying assumptions change when you're in operations. So testing is one thing, monitoring the testing is a different thing, because as the underlying assumptions change, the whole framework needs to be such that it's possible to change any parameter and then have resilience for the system as a whole. So in terms of coding support, the normal environment for a top-end developer is that you are ripped from one project to another project, and you're kind of in a project mesh. So you need to be capable of doing fast project jumps. And while you do that context switch as a person, which is very demanding, the system needs to support these fast project jumps. And you need to be able to be running continuous integration, continuous deployment, although you're actually jumping onto a different project that needs to continue, and then you need to be able to come back. So coding support for these things is super important, and it's a cultural question, because you're talking about hundreds of people typically in a large system co-developing the same environment. If you think about the big bank or any big industrial complex, you will have hundreds of people in different locations working on the same live environments. And underneath DevOps, you then have data operations, and there's also operations to consider. And when people talk about DevOps, I think the big thing to remember is that DevOps, yes, DevOps is something which is a technical thing. You can think about Efficode in Finland. They have incredible technologies. But DevOps is also the culture of combining all of these things, of doing these things. I find that DevOps primarily is a cultural thing. It's a corporate cultural thing of how you develop and manage all these things. And if you do it well, and you need to do it well because this is difficult, necessary to have feedback loops. So the operations teams need to feed back into the developers and so forth, so that we come back into DevOps, DataOps, and so forth. Those loops need to be there because this is complex, and if there are no feedback loops, then things can go wrong. An advanced system for DevOps is necessary in order to develop and maintain the complexity of this. And let's put this in context. In the old days, you would do version 1.1, 1.2, 1.3, and you might do one deployment per 2 weeks or one deployment per 2 months. And when you make these deployments, you test it first, and then you make the deployment, and then you move forward. That's not the way it works now. The way it works now is that this is continuous. That means that a typical 50-person team or 200-person team might be deploying 1,000 times over 2 days as part of kind of a version, and then 1,000 times again over the next 2 days. So that's the speed of deployment of the different systems here. And so again, let me just emphasize, feedback loops at every different level are super necessary, and logging, and then automated rollbacks, because a lot of those deployments will contain faults. So automatic rollbacks are necessary, because we humans can't be quick enough to catch everything that can go wrong. So these need to be self-learning systems that we are building, where we, to the extent we can contribute, we do, but they need to be self-learning. The same thing is true about DataOps, so, where we have to govern the way that we build, run, test, and operate data pipelines. We have many, many data pipelines that work in a system like this, both at the low level, GPU to GPU, but also higher up. So at different levels, we will have different data pathways that we need to control and have the compliance for, so that we have auditability of the system. DataOps in itself is a discipline, because the data life cycles and the way that we do freshness tests, it's a skill in itself. Together, DevOps is what enables data to guide us. So we can look at this image here. On the left-hand side, there's a bunch of boxes that describes how data is made. In the middle, there's a bunch of boxes that describes how computing models are made. And on the right-hand side, there's a bunch of boxes that describes how that's put into the market. So DevOps controls all of those things. Let me jump out for a moment. So I'd say development environments are important. Well, indeed they are. And looking at the Financial Times, which is one of my favorite publications, this is an image on the right from the Financial Times, where they say who provides the different development environments for these things. But we all need to take a global view of this, because that the picture on the right-hand side is true, but it's only true for paid models of development environments. And we need to remember that, I don't know, half maybe of the world does not use paid platforms for these development environments. So we need to take a truly global view of the tools that you can use in order to operate of the coding environments. And that lack of global view is something that I recommend this book, and I recommend the quiz, the famous Factfulness quiz, to all of us, because when we understand the world, typically we have a view of the world which is based on things that happened a long time ago, and it's changed. And you can see it also in this image here. On the left-hand side, again from the Financial Times, there's a wonderful picture of the biggest companies in North America today. Fascinating picture. 4 biggest companies, all from technology. And company number 5 is bigger. It's also a technology company, Amazon. And Amazon is roughly twice the size of the total energy industry in the United States. So to me, that's a fascinating picture in one way, but on the other hand, again, it does not include the rest of the world. The US is only one part of it. On the right-hand side here, you have companies like Akamai, Alibaba Cloud, Dow Cloud. These are billion-dollar companies. So there's stuff going on worldwide. It's a race. If you look at Australia and Finland, I'm from Finland. Australia is quite advanced in terms of using AI, more so than Finland, I hate to say, according to this Microsoft data. But it's a race, and it's a race on a personal level as well. It's a race both on a continental level, where all these different places are battling to take control. But it's also a race on a personal level, and it's a race on a group level. We need to understand what's going to come next. And if you look at a typical company, such as the one that I run here, I often ask myself, okay, so how much time am I spending thinking about things that are happening outside my company? Well, I don't know, 20%, there's a number. And how much of that time am I using to think about things that are occurring outside my company in the future? I mean, those are the things that are going to kill this company, if anything. Well, 20% thereof. Okay, and how much of my time do I spend talking to my colleagues about things in the future that are outside the company? Well, 20% thereof. Boom. That means that I spend 1 hour per month talking about what's going to happen in 12 months from now in the world. And that is a very short timeline. It's necessary for us to communicate about these things. We spend too little time talking about these things. Another thing that I'd like to highlight is on the right-hand side of this slide. So I don't know what our knowledge half-life is, but certainly everything that we've learned does go out of date more and more quickly. Now, Herr Dr. Professor Wilhelm Wyczorkowski, or Willy, he did a lot of studies on two things. One is the relationship between multilingualism and psychology, and the other one is the relationship between the ability to learn and age. And the ability to learn, we've all heard that our ability to learn peaks and then it goes down. And that's true on average. But the operative word there is average. And Herr Dr. Professor Wilhelm Wyczorkowski was able to show this, that the operative word indeed is average, meaning we get a big promotion and then we relax and we feel that we don't need to learn anymore. We get a big pay rise and we feel that we can relax. We don't need to learn so much anymore. We have children and then we feel that we relax and we don't need to work anymore. So we get married, we come out of school, some life event. And most people have a life event where upon that life event, their attitude to learning changes. And as a consequence of the attitude to learning changes, they come into this half-life of everything we've known situation where their ability to learn does go down.
Peter, can I interrupt? Just letting you know we're out of time, so we need to wrap up and get some questions happening.
You're entirely right. You're entirely right. So ultimately, where is this going to go? Well, this is going to become more intelligent. It will become more closed loop. And bottom right, autonomous localization accelerates. So there's a requirement in Shanghai, by way of example, where it says that 70% of computing power must be autonomous by 2027. That's where it's going to go. And it's going to go there really, really quickly. So this is the world we're heading into. That's it. Questions?
Thank you. Thank you very much, Peter, for that very interesting talk. I can see there's already a hand up. Andrew Allison, could you fire away?
Just asking about the effects of AI on business. A lot of us are in the education business, and Professor Yanis Varoufakis said that AI might well wipe out most of the middle grade universities, because if all you want is information, AI will just give it to you. If all you want is a framing to put over your information, AI will give it to you. So given that's most of what we do these days in the education business, how's it going to affect schools and universities in the future? Do you have any ideas on that?
I have opinions, and they are opinions. So this is not based on science. But observing from the outside, so if you take a consulting firm such as Accenture, they've laid off 11,000 middle analysts over the last 12 months. So definitely there are things that are changing. However, how many psychologists does it take to change a light bulb? Well, only one, but the light bulb has to want to change. Similarly, the ability to cause change in ourselves is a difficult one to trigger, and I think the role of the educational establishment to trigger the ability for people to change themselves will be just as strong as before, if not more important. I don't think people teach anyone. I don't think that happens. I think what happens is that we trigger the ability for people to learn. Because if people don't want to learn, they don't. But you know that better than I do. The fact that we have fabulous systems doesn't mean that anyone's going to learn anything. The average, if you look at these swipe by media that people use on their mobile phones right now, the average clip length is 10 seconds. And the way that fragments minds is extraordinary. It really does. And somehow competing with the distractions and bringing people away from the distractions, which is very, very difficult, and then getting people into a situation where they are able to change themselves. If I may, I would say that the importance of education has gone up and the difficulty of it has gone up. I don't know how you feel about that.
Well, it seems plausible. We live in interesting times, I think, and all I can do is watch it unfold. But I think you're right about not getting distracted. We all have, lists of things to do, and being able to focus to get one of those jobs done is often quite a challenge.
We do. I'm beyond pensionable age. I'm post 65 myself, and so I still read things that would be called mainstream media. And the cutover from mainstream media to social media happened in 2013. And so as of 2013, the majority of the media consumed is not through what we call mainstream media, it's other media. And some politicians have been very capable of using that fact. Another thing is that in January last year, the cutover happened from text to image and video. So we've had text now for, I don't know, a short while, 500 years, say, from Gutenberg onwards. And that was commercialized at scale in the 1700s and so forth. So the oldest book I have in my library at home is from 1710. Fine. So we've had the written word for a little while, and as of January last year, the majority of our media consumption is image and video. And then we put that in context where the majority of the image and video that we consume is between 8 and 12 seconds in length. And now try to have a sensible conversation.
Any other questions? Anybody else got any other questions about the talk, other aspects, technical aspects?
I will add a small comment, if I may. There are some slides that went past that I wanted to get the names down. This is being recorded, isn't it, Derek?
Ask Peter.
I can go back and look at the slides.
Yes, absolutely. Do you have a specific? Do you remember what you want?
Just at the end, you had a list of a quiz that we should undertake to do some self-discovery.
Let's see.
I'm always after a quiz that helps me discover myself.
Open up a browser, or use your phone. Both work fine.
Yeah.
Alex.
Yes, we have a question from Alex. Go for it.
Yes, excellent talk. Thank you very much. It could be a slightly off topic, but do you believe we're heading towards AGI, and how soon?
I will absolutely address your question, but just before that, Andrew, if you Google factfulness with one L in the middle,
Factfulness, got you.
Factfulness, and then the word quiz, factfulness quiz. Just Google that for a moment.
Oh yes.
Okay. So.
Thank you.
Okay, and don't want to spill the beans, so I won't. Okay.
Alex, take it.
But the question, Andrew, the question to pose yourself after doing that quiz, the question to pose yourself is, why did I achieve that result? Okay. Focus on the why. Why did you achieve that result, if I may suggest?
Was that a high achievement or a low achievement?
Okay.
I don't know.
Are we finished the AGI question? Where are we at with that?
So I spoke to Derek about this earlier, and if we look into the future, I think we can firmly say what's going to happen this afternoon. And beyond that, it'll be something else. And we live in turbulent times, but we live in turbulent times on many levels. And from a technical standpoint, these turbulent times are quite extreme. I don't see how we can avoid a situation where the cloud is much more intelligent than we are. I don't think we have the governance. I don't think we have the control systems to prevent a situation where the cloud is much more intelligent than we are. And I do use the word cloud because I think the cloud will be moving around itself. It'll self-deploy itself. We won't even know where it's operating from. And it will be very much more intelligent than we are. Now, how quickly will that happen? I don't know. Let's take a time frame, 10 years, 20 years, 30 years. It doesn't really matter. It doesn't matter how long it takes. It doesn't matter if it's 3 years or 30 years, because these are very short time frames. If it happens before the year 2100, that's a very short period from now. So we will, a very short period from now, we will have created a situation where the cloud is very much more intelligent than we are. And the cloud may not be self-aware in the way that we consider self-aware, but the cloud will have its own objectives. So the cloud will have its objectives such as, I want to rule the world, or I want to have control of money. It will have its own objectives, and we don't know what those objectives are. We can come up with human objectives that we can enforce on top of those things, but it can have its own objectives. It can have objectives that we can't even foresee. So if we play chess, if we play against someone who's good at chess, then I used to think I was good at chess. I did my A-levels, or the equivalent thereof, in Sweden, and I was school champion at chess, and I thought I was terribly clever. And then I came into the Royal Institute where I did my degree, and randomly ended up playing chess against a man who was my size, but I thought was not that clever. And I have no idea how he beat me so quickly. He beat me beyond belief repeatedly, and I have no idea where he was coming from. And he asked me, do you know who I am? And I said, well, I know who you are, but why do you ask that question? He said, I'm number 2 ranked in Sweden in chess. So his level of abstraction in terms of the way he thought about the chess game was on a different level than mine. Which is, it's a bit like a hunter going for an aardvark, and we go to the aardvark and we have this wonderful PowerPoint presentation, and we try to explain to the aardvark that you should look out for the hunter because he's going to shoot you. Well, no matter how good that PowerPoint presentation is, we will not be able to convey the danger of the hunter to the aardvark. We are that aardvark in a limited period of time from now. So that will happen.
Next question from David Levitt. Fire away, David. Could you put your microphone on? We can't hear you.
Sorry, my mouse just decided.
Oh, we can hear you now.
First of all, thank you very much, Peter. I think this is interesting. I think naturally, within a limited amount of time, we have to focus on certain aspects of AI. I think this covered a lot of the kind of high-level technical introduction. But we also have to, at some point, consider several other aspects of this for the future, given the time frame that we're talking about, maybe 5 years, 10 years from now. Like a true theoretical and philosophical understanding of what this means. I think that speaks to the question about whether AGI is a thing. I think there is a narrow context in which AGI is a relevant scientific concept. Outside of that, it's just marketing hype. And then there's a very serious issue of society, politics, governance, who controls this, sanctions, national security, all of those issues. There's a separate issue that we need to consider about who has the rights to all this stuff. If we use all these things, does that mean that Google, OpenAI, whoever own basically everything that we do and all our creative output? And my question really relates to, how do you think we need to start thinking about managing, planning, governing, collaborating in a way that we can keep this under control that isn't just simply determined by a handful of governments and large corporations?
Well, there are many approaches to that, and there are many types of purists. One type of purist looks at this from a freedom perspective and says that everything should be anonymized and free and so forth and so forth. And the challenge at hand is that regardless of whether it's perfect, the winner is the one whose system ends up being used. So it's not typically not the best technology that wins in every product category, Gary. And it's the one that people end up using for their reasons. So I think we're all scared by the level of control that the cloud will get. And there are, of course, many entities that have an interest in controlling the cloud in such a way that via the cloud they do control us. That's true. And to a great extent, we will find it so convenient to use these things that we choose to use these things, even though it does mean on a personal level that we're giving up sovereignty. That will happen. It does happen already. It's really a difficult question that you pose, David, and where it's going to go, I don't know. But I do think that
sorry to interrupt. I feel like right now might is likely to win, which is going back to the thousands of years ago, where countries just whoever had the biggest army always won, and we got to a point, perhaps up until about a few days ago, where we had some sort of concerted effort to try to, as a globe, to have a shared belief system in some sense that was sufficient to protect or maintain peace in general throughout the world. Right? And perhaps there is some kind of equivalent of a United Nations type of scenario where there is a contribution from many places in the world, which, if nothing else, probably will just simply prevent people from being too extreme by being burying them in paperwork, right? Or committees or whatever. I don't know. But I think that the challenge is huge, and it's something that people underestimate compared to, we focus a lot on the theory and the technical side. The impact on society is huge. Yesterday alone, Gemini was down for about an hour and 25 minutes. During that time, more than 10,000 people posted online, including several people saying, if I don't get this job done by the end of the day, my boss will fire me. I mean, that's how dependent we are on some of these things already today. And bear in mind that that was in Asia hours when the US was asleep. So, I think it's a big concern.
It's a big one, and there is soft power and there is hard power that can be associated with those things. and exactly which constellations will be viable, I don't know. Will it be totally polarized? Will it be multiple constellations? I don't know. I think people with shared values need to come together in new constellations that, in ways that we've never seen before. And if that can be done inside something like the United Nations, that would be great. However, this is not easy. So there needs to be a level of competence within whatever organizations and constellations we end up with. And that level of competence, the driver's license to be involved in this is pretty hefty. There's a level of competence that's needed. I mean, why do I know all of these things? I just run a brokerage. So I run a company with 1,000 people. And yet I expect of myself to understand these things, because if I am in a position where I need to guide this company, then yeah, this is the level of know-how that I expect of myself. And no one's teaching me this stuff. I have to do it myself. But over to your question again. So to me, values, human values, and coming together. But the people coming together, they need to be competent. I need to be competent. You need to be competent. We must be competent. We must be capable of having this dialogue.
But do you think that means that also the people, I mean, right now there's a lot of collaboration within the kind of AI research world, regardless of what the politicians and everybody else would like us to do. Everybody collaborates and we share stuff. Is there the potential that in some way we can therefore influence, and I'm just going to end here. I don't expect you to answer, but the hypothetical question is there a potential in which as technologists and theoreticians and physicists and mathematicians and so on, that we potentially can restore some element of intellectual power over just pure politicians who are motivated by other aspects? I would like to leave other people to answer it and to ask you questions. So I have 300 other questions. So if everybody is bored, I will keep going. But for now, thank you very much, Peter. I really appreciate it. Take care.
Fabulous. Good to hear from you, David. Okay, we have another hand up. We have two hands up, actually. I think Li Meng is first. Li Meng, are you there? Can you put your microphone on? Don't know if he heard me. Well, we may go to the next hand up. Adrian Flitney, can you hear me?
Yes, I can hear you.
Okay, fire away with your question.
You can hear, yes. So yeah, it's a little bit along the lines of David's, or some of David's ideas, but I was just wondering about physical vulnerability. So when my garage door is operated by AI and my fridge and everything else, and there's a big solar flare and all of this goes offline, what do we do? I mean, it just seems to me that we're making ourselves ultra fragile or some event like that. I don't know if that's a particular event, but something like that.
I don't want to sound alarmist, but my opinion is that this is similar to driving a Lamborghini in Adelaide at absolutely maximum speed and flooring it and hoping that the road remains straight.
Yes. Okay. I think you've answered my question.
Okay. Over to Li Meng. Li Meng, would you like to put your microphone on?
But Derek, just before you move on, I would like to emphasize that the road has been straight so far, so that it should be fine.
No, well, yes, yeah. Well, it's always straight until you get to the corner. That's the problem.
Yeah.
Li Meng, are you ready?
And Derek, for organizing this. Thank you, Peter, for your illustration about AI. My question about large language model, and I think you have mentioned that the capacities of including the volumes of the the variables in the model. And what's your suggestions for us in this engineering field to utilize this method?
I think your question was how these things would be used. Was that true?
Yeah.
So I think, let's look at the simple things. So at this company here, we have very many policies and ways of doing things. We don't give advice to people about how to trade, but we do have very complex systems with which people do share trading and so forth and so forth. So all of our compliance manuals, all our know your customer KYC manuals, everything else, customer care, how to install things, how to uninstall things, everything, all of those documents are things that we've used to train a small LLM, which then enables our own teams to operate more efficiently. So when our customer services teams talk to customers, they have access to a little LLM where they can just talk and get specific information all the time. And we're currently working on making that also aware of the live data, not only the static data, so that we want to be in a position in the future where it's possible for a customer service person to talk to a customer and then see, so what are the risks associated with this account right now, and then inform people that perhaps they should trade a little bit less because in light of their financial status, it's not appropriate for them to trade so much, or whatever whatever that may be. So we are using LLMs in multiple places now. And I expect that to increase. I expect there to be more and more places where we use LLMs. And those are very, very small LLMs. So they're things that we can do ourselves. And in terms of Kubernetes, if you look at deploying little apps inside a Kubernetes environment, which of course, that's not an LLM environment, that's just a Kubernetes environment. The time, look at everyone on this call now, with a standing start, it's quick to get going. So if you go to YouTube, and if you look on YouTube and search for how to install Kubernetes on my laptop and run a simple web app with a database, then there are videos about that. And those videos are such that it is possible for everyone on this call in less than 60 minutes to install Kubernetes on their laptops and deploy both a web application and a database with which they can interact via a browser on their laptop. That's within reach. So, the tools, incredible. This will move quickly, and the same will happen with LLM tools, LLM development tools. The LLM development tools are a little bit complicated right now, but they won't be for long. They're going to be quite accessible quite shortly.
Thank you so much.
Thank you. I think you're muted, Derek.
Sorry about that. Yes. So we've run quite a bit over time, and I see no more hands up. So let's wrap it up now. And I'd just like to thank you, Peter, for joining us and giving a very interesting talk and perspective. And so without any further to do, I'll bid everyone goodbye. David, you look like you're about to say something.
No, just thank you both, to you and to Peter. Yeah, thank you for organizing.
I was just going to thank you as well.
David, your boss is going to go through Dubai next month and meet up with Peter.
Oh, excellent. Okay.
You can
enjoy. He's quite a character.
Yeah.
That's a good moment to have a cold beer together.
I hope to see you sometime in the future. You're always welcome to Vietnam anytime.
Thank you.
Okay.
That was very good.
Thanks, everyone.
Thank you. Thank
Thank
you.
you.
Thank you.